Hello, hello, hello. Welcome back to Kerbal Space Programming Part 5. I'm Kevin here, and in the last episode, we had launched our first satellite into orbit. And this has got its little antenna here and all these batteries and its CPU core. And since we last left off, I have put 3 more of these in orbit using the exact same script. That's the cool thing about pre-programming all of this, is that I can just kind of jump back into the vehicle assembly building, make a copy, and do the whole thing again. So we actually have 4 satellites in orbit. And now that we have these here, this is actually kind of helpful because I can kind of explain what it is that we're trying to do. So we see that there's these lines here, and this is coming from Remote Tech. Let me just reposition, and we can see that it's actually drawing these lines. It's drawing it to OmniSat 1 and to OmniSat 2, and you see the orbits ended up pretty similar to one another, which is, it's not perfect, but it's pretty cool. And what this means is Remote Tech is set up so that we can only control and get access to these satellites so long as we have a line-of-sight connection with the Space Center. But we can also use these relay satellites to bounce the connection between these 2 satellites. So let's see, which one are we on now? Satellite 4? Yeah, so if we time warp ahead a bit, we'll see that this goes out of range because it's going under the horizon from the Space Center. But if we time warp ahead, and there we go. Now we have a direct connection to the Space Center. And if we were to bring up the KOS terminal, let's open this up, open terminal. There we go. We see we've got this green light here showing us we have a direct connection. We could type in stuff, print, hello, I have a connection. And it does that, which is great. But as soon as we fall out of range, then we will be in trouble. And unless, this one happens to be able to kind of bounce the connection, and it looks like it is not. So yes, and I think I can toggle what's being displayed. No, okay. That's not doing that. But what we want to do now, because okay, there we go. So now that one has a connection. But what we want to do is boost these up into a higher orbit, because once they're in a higher orbit, then we can most assuredly boost things around. Okay, so here we have kind of an approximation of what we've got. We've got 4 satellites in orbit, and they're rotating around, and we have the Kerbal Space Center marked here. And whenever these are in range, we have a direct connection. And this is important because it means that we can access the terminal and load up new commands to run. And it also is critical for transmitting science back. If you don't have a connection, you can't transmit science, which is going to be a problem for us. Now we want to make sure then if we have something that's on kind of the opposite side of the planet, then we have a problem. Because if we try and do a connection, well, this is going right through the planet's surface, so that isn't going to work. Now, if we had these in a, if this were kind of positioned here, then we're going to be fine, because while we can't, do a connection like that, we can relay between these 2 satellites, and so we should still be able to control this craft. But because this orbit is so low, we're kind of limited. So what we want to be able to do is actually boost these up into a higher orbit. So let's imagine that we got these out here, then we could go ahead and say, bounce to here and then bounce to here. These are going to be moving much more slowly. And then, if we had some other mission that we were sending that was on the other side of the planet, well, that's perfectly fine, because we can then just relay all the way to here. And we've got a direct connection, so we can still access this, even though it's on the complete other side of the planet from where we're at. So let's remove these. There we go. So what we need to do in this episode is work on actually boosting up to this orbit. We're going to do this with a transfer. We're going to do an orbit like this. So let's kind of get these all bunched up out of here. So when we get to this point, and this point doesn't particularly matter at first, we're going to boost up our orbit, drop out of low orbit, and go into this transfer burn. Okay, so then we'll coast up to this new apoapsis, and then we'll complete our burn, and then, we can orbit around this way, which will be great. And Photoshop is helpfully throwing all these offset values, which is wonderful. So for this first one, our script should be pretty easy. We're just going to, burn until our apoapsis is a certain height, and then we'll wait till we're at the apoapsis, and then burn until our periapsis is the same height. So this bit will, oops, nope. We'll just wait until this end, kind of pops out over here. But for this second one, we're going to have a bit more of a challenge, because let's imagine that we got all these out here and they were all, they're all up here. Well, then we've got an issue. Then none of these have a connection. What we really want, we can't draw a line to any of these because they are below the horizon to Kerbal. What we want to have, ideally, is to get these evenly spaced out. So we'll have one in the back, one over here, and one over here. And then these can all rotate at, approximately the same speed. And so kind of regardless of where these are at in their orbit, we should be able to get a connection to all of them. And just as importantly, we could get a connection to something inside there. So, we'd have a connection from here to here, and then if we had something in a low orbit on the other side of the planet, we could, say, that's fine. We'll just connect to you like that. So what's important for us to figure out is once we have our first thing on this high orbit, right? And I got to move these down. Where's our low orbit? There we go. They're on the low orbit. Yes. Okay, so we've got these three on the low orbit, and we need to figure out, okay, so we are going to go halfway through this transfer orbit and then circularize. And while we are traveling up to our apoapsis, this thing is going to continue going around its orbit. So what we need to figure out is how different do our orbits need to be so that we can fire at the right time. Because we want to make sure that, if this is, if this is, here, then when we get up to here, how much will this have gone? Is it going to be here? Is it going to be here? Probably not. And we could do some complex math to figure that out, but what I figured out is that basically we want to be approximately 10 degrees ahead when we start our burn. So, like there. And then by the time we get up here, this will have made it to, I think, about here. I think I'm explaining that right. So that's what we're going to script today, and then we're going to get these satellites into their positions, and let's jump over to the code and look at that. So enough of that orbital mechanics junk, let us jump into our circularization script. So remember, in the last few episodes, we've talked about functions, which are kind of groups of shared code. Now, we're not going to be using those, but one of the things that we talked about, my function, there we go, function, my function, is parameters. And parameters are arguments that we can pass to the function. So we could say parameter message and print message. And then we could call this function by saying my function, and then inside parentheses would say, hello. What this is going to do is it's going to say, okay, I know I'm a function and you called me with this parameter, and then I'll go ahead and use that parameter in the rest of the code. Now, in addition to functions accepting parameters, we can actually let scripts accept parameters as well. So we've got this script, which I'm calling circularization.ks, and we can call this inside Kerbal Space Program by saying run circularization, larization.ks. And we can pass it an argument directly inside parentheses like this. So what I'm actually declaring here is that we're going to say we accept three different parameters: a target altitude, a reference vessel, and a longitudinal difference. We'll skip over the last two and kind of go to that last, but this target altitude is, okay, well, we've got our current orbit. What is the orbit that we want to get up to? And when we launched our scripts, we had them at something like 70,000 kilometers up. Wow, I can type. Okay, 70,000 kilometers. I think what we want to do is we want to get them to about 1,000,000 meters. So 1,000 kilometers up. And that should give us enough to get our angle right. So this stuff is all about those angles between the vessels. So we'll skip over. Yeah, we'll skip over both of those for the moment, and let's just jump down to the sheer logic of what we're doing. So we have kind of these three steps. We want to do our transfer burn, so get up into that orbit that's going to take us to the high point of the outer orbit. And so what we're going to do is we're going to say set transfer to prograde and then lock the steering to transfer. Now, in the past, we had done some stuff like, lock steering to heading 90 degrees or lock steering to prograde or things like that. But the problem with doing that is that as we start the burn, the prograde vector, now the prograde is the forward direction in our orbit, the prograde vector is going to change as we burn. So we don't want to say lock, because what lock is going to do is it's going to say anytime that I need to figure out where I'm supposed to be steering, then I should look at the prograde every single time. And this will run, kind of every multiple times a second. So what we're going to do is instead say set, and this gives us a variable. If you're familiar with any other languages, it's like saying, x equals 5. We're going to set transfer to prograde, so like set x to prograde. And this means that this x value, or this transfer value, is never ever going to change. It's just the prograde at the time that it looked at that code. And now we'll say lock steering to that value. So the steering is always going to, if the prograde happened to be something like, 5, for example, then anytime that we want to know where we're supposed to be steering to 5. Of course, it's not 5, but we'll lock the steering to what the prograde vector was. Then we'll wait 5 seconds to make sure that we're able to turn the ship around if we have to do that. We'll throttle all the way up. We'll wait until our apoapsis is greater than that target altitude that we passed in. The target altitude times 0.9. Because what I want to try and do is make sure that we don't vastly overshoot. And if we're going full throttle, then this can get iffy. So we're going to wait until, if the target altitude is, 10,000 kilometers, then we'll multiply that by 0.9 and say, okay, we're going to wait until, 90,000. So 10,000 kilometers, 1,000 kilometers and 900 kilometers, right. Then we'll lock the throttle down to 0.1, so we're going to just do a little bit of thrust, and we'll wait until we're actually above the target altitude. So this is just kind of stepping down our throttle so that we don't, vastly overshoot our target. And then we'll lock the throttle to 0. So then we've got that transfer burn up to the higher orbit, and we can wait until we get there. So we'll wait until actually I had this in for debugging purposes so that I could do some time warping, but it's not necessary. So we can just say wait until, there we go. That's easier. Wait until the ETA to the apoapsis is less than 20. We got to get rid of this. Yes, there we go. So we'll coast until we get to the apoapsis, and then we've got to do our circularization. And this is almost exactly the same as the transfer burn. We set this circularization variable to prograde only that one time. We'll lock the steering to that value, wait 5 seconds so it can turn itself around, lock the throttle to 1, and now we're just going to wait until our periapsis, so that's the lowest part of our orbit, is greater than the target altitude times 0.9, throttle down to 10%, and then wait until we hit the target altitude, and then we're done. Okay, so this will actually be enough for our first craft, because we don't necessarily care when it does its burn. But we want to make sure with the second and third and fourth, these ones, we need to make sure that they only do this transfer burn when they're in the right position. So that's what we've got this currently commented out stuff for. Let me just get rid of those. Oops, there we go. Not that. That yours still a comment. Okay. So in addition to passing in the target altitude, we're going to pass it in a reference vessel and a longitude difference. So what this is going to mean is that, when we run this on OmniSat 2, instead of, first we've got this if condition, because if this if condition fails, then we'll just skip over and do our transfer burn right away. So for the first OmniSat, we'll just say run circularization.ks, and we'll pass in our target altitude of 1,000 kilometers, and we'll just say false and false, because we don't care about your longitudes and your references and all of that junk. Okay, so that'll be for the first one. For the second one, polarization.ks, we want to get to the same altitude, but this time we're going to say, take a look at OmniSat 1, please, and make sure that you are 10 degrees ahead of it before you do your circularization. Okay, so if the reference vessel, and this is syntax for not equal, so if reference vessel not equal to false, now we're going to do our weight stuff. So we'll say we'll set the longitude difference to 0, and then we're going to wait until the longitude difference. Oh, hang on a second. Yeah, I've still got this hard-coded. Longitude difference minus 0.5 and longitude difference. Let's see. Yes, longitude difference plus 0.5. Sorry about that. Yep. Okay. So what we're going to do is we're going to say wait until the longitude difference is greater than the argument that we passed in. Wait until LNG diff is greater than the longitude difference that we passed in, minus 0.5, and LNG diff is less than. Yeah, there we go. So all we're trying to do is wait and make sure that the difference between, the current difference in longitude between those two crafts is about what we passed in. So if we passed in 10 as our argument, which we have in the second example, then we're going to say, okay, wait until the difference is between 9.5 to 10.5 before doing this stuff. Okay? So in here now, we're going to set the longitude difference to our current ship's longitude. This comes from KOS. It's a helper function, and it'll give us a value between negative 180 and to 180. There we go, to 180. And then we'll say, again, take the difference between that and the vessel. This is another KOS thing. We can actually get information about other ships that are in orbit. So we'll say vessel, and we'll pass it the name. So this is another function. And we'll say, and I want the longitude of that. So if our current longitude is 100, and the other ship's longitude for Omnisat 1, let's say that they're 50, well, then we're going to set LNG diff is going to be 50. And then when it checks this, that's not going to work, because we want to make sure that it's within an acceptable range of what we were waiting for. And then we'll just wait, a tiny little bit, so we're not constantly looping over this. So what this is going to mean is that we can just run this and say, okay, wait until you're 10 degrees ahead of Omnisat 1, and then go ahead and do your circularization. So let's jump into KSP and actually do some space. And here we are back in space, looking at Omnisat 1, pointed in the probably the wrong direction, but that's okay. We've got some steering logic in our script. Let's pop open the terminal. By the way, you can right-click to open the terminal, or you've got KOS here, which shows the current stuff. Let me close that up. And wait, are we actually able to type stuff in here? We shouldn't be, because we have no connection. Print hello. Okay, and there we go. It says signal lost, waiting to reacquire signal. So it's not gonna let us. Let's take a look at the map. Oh, we're on the complete wrong side. That is not fun. But we see we do have a connection to Omnisat 2, which isn't really helpful. But, oh, look at that. Now we actually do have a signal. Oh, and it printed hello, because we're bouncing the signal. This is what we want to do, but from a higher orbit, so that we have much better angles. But you know what? Since we've got, well, now let's go ahead and jump ahead, because I'm just nervous that we might lose this signal if we try and do stuff right away. So, okay, there we go. We've got a full signal. Let's go ahead and copy our circularization. Or was it circularized? I think from 0 from the archive. Good, okay, that ran. And now we'll go run circularize.ks, and we'll say, I gotta make sure I type this correctly, or we're gonna end up in the wrong orbit. 1 million false. And go. Let's jump out a map view so we can watch this, watch our first circularization script run. Okay, good. It's turning. It's locking to the prograde vector. And there we go. We are burning. Jump back out to the map view. And this is going up and up and up, which is great. And, okay, now we've slowed down because we hit 900. And there we go. All the way up to 1,000 kilometers. Now, we could try and go higher. There's certainly a lot more space. I wanted to be a little conservative because, we are running on somewhat limited fuel, but and so I wanted to make sure that at some point we want to be able to possibly decommission these satellites without having to do some crazy rendezvous. So these should remain with enough fuel to be able to deorbit. And now it is just a matter of warping ahead until we get to our apoapsis, and this is going to take a little bit because as you get higher up in your orbit, you are moving slower, naturally, because you're covering more space, and don't want to time warp ahead of this because that could throw off our orbit, but finally we managed to get there. Oh, there we go, and it is like, that was a weird way to change your steering, but okay, I like it. Yeah, so KOS has its own kind of lock steering stuff, which is not always the most effective. But there we go, and it's just finishing up, hopefully. And it is rocking back and forth. Okay, program ended. Let's take a look at how we did. Jump out into the map view. And now the periapsis is here, and the apoapsis. Okay, so our apoapsis is higher than what we probably wanted. This is part of because as we push stuff up here, then this was going to change because we weren't exactly on when we burned. And, so there's some additional math that we could do to get a more exact orbit. And so over time, these will kind of phase out of alignment. But that's okay, because by that point, we should have even cooler satellites that are able to do even cooler stuff.
And having waited for satellite number 2, or having switched to satellite number 2, we have to wait until we actually get a signal so that we can pop open that terminal and copy the script over, at which point we'll enter the same commands, but we'll give it that reference vessel and see what happens.
Now, this is something that I ended up trialing and erroring on a oops. Nope. Now we got a problem with our script, which only occurred when it got into that if loop. Let's jump back over and see what we can figure out. Okay, let's look. Okay, yes, I see the problem here. We have vessel other ship, and that is wrong. How embarrassing. We changed so I was running this on kind of a test script and then expanded this out. Reference vessel.
Yes, so I had gone ahead and used the wrong variable name because I had switched the script over, and I try and tidy these up before make videos. But now it seems that we have gone out of signal range, so we have to wait until we get close there again. And again, we're just trying to make sure that we don't time warp too quickly, because if we pass the correct point, then the behavior may be a little bit unpredictable. But hopefully we're getting very close now, confident that there will be no more errors. And let's see what happens now.
Oh, nope, we got another bug. We have another bug. What's going on? Undefined variable oh, there's another typo, guys. Oof, this is not going to be this is an embarrassing episode. Let's jump back over to the script. Yep, okay, here we are. When we refactor this, I typed long diff instead of LNG diff. That's not good. Okay.
So yes, additional bugs, and this is actually kind of reminiscent of the old programming days, because it used to be that it would take you, you go ahead and write some code, and then you would tell the computer to compile it, to translate it from the human code into machine bits and bytes, and that could take, 10 to 15 minutes, at which point it would run, and then you would discover, nope, there was some tiny thing that you had to change, so you'd make your change, and then wait another 10, 15, 20 minutes, and test it all over again. But thankfully, we have fixed all of the bugs in our code, and we can let this thing go up to apoapsis and circularize. You see, the orbit is not entirely similar. These will eventually drift out of alignment, but because they are kind of short-range satellites, it's not the end of the world if they are not completely perfectly spaced. And as we see, we're just wrapping up that burn, and OmniSat 2 is in orbit. So yes, we run the same thing for OmniSat 3 and 4, and here we're seeing the last satellite finishing up its circularization burn, and we see now we have all of these perfectly, or at least somewhat perfectly evenly spaced, and they're going to drift a bit out of alignment because their orbits are not entirely the same, but it is okay. What this means is that we will be able to send craft completely, to the dark side of Kerbal and still be sure that we're able to have a connection, because we can bounce things off. And this will be really helpful because once we have new missions, we won't necessarily be programming the entire mission all at once. We'll say have a script that gets it up into orbit, we'll connect it and say, okay, now go to the moon or go to some other planet. And we can do cool stuff like that, but it's important to make sure that we have a connection to do that. And yeah, I love how this looks, and we can see if we time warp a little bit, we can see how this kind of rotates, and it stays, the shape will change a little bit, and we can run our next missions and do cool stuff in the next episode, so I will hope to see you then. Cheers.